All right. So for the last part of the day, we're going to have Shlyakhtenko from UCLA, and he's going to tell us about what it was to experience. Take it away.
All right. Thank you so much. I hope you can hear me well. Well, it seems that I can't really hear you. Oh, now I can hear you. So first of all, I really appreciate the invitation to give a talk. I really apologize for not being there because unfortunately the timing, it was postponed many times and it coincided with a conference where I had to be at UCLA at Lake Arrowhead here in Southern California. But it's a great opportunity to be able to talk to you. So I gave this title, and I realize it's awfully ambitious to do this in 50 minutes. So I will do as much as I can, and at least hopefully you will be entertained, right? And I know you have a banquet coming up later in the day, so hopefully whatever I do wrong will be forgotten. So let me ask first the following question. So suppose you are in the classical case. So in the classical case, you have some sub variety, sub manifold, subset, whatever, inside, let's say Rn. So you have some algebra functions, let's say maybe continuous, or let's say continuous functions on X, or maybe measurable functions on X with respect to some measure. And so these are functions on your set. And what you're interested in is making sense, how to make sense of dimension of X. Oops. And there really are many ways of doing this. So let me talk about the nicest case. And that's where X is an algebraic variety. So basically, you have, it's presented, or let's say the algebra of functions on X. These are, you can describe this as a ring where certain relations are satisfied, right? So you have some equations, you have your coordinates, say x1, xn, they are coordinates on X. But then you have some relations, let's say R1 of x1, xn, Rm of x1, xn, they hold true, right? Some equations are true. And so that describes your set. So your set is some nice thing like this, say a two-dimensional surface or something like this sitting inside R3. So how do we make sense of the dimension? Well, there are several ideas. Dimension X. Well, tell me some of them. Let's see if we can make this somewhat interactive. Or it's not technically possible for you to speak when I speak. All right, since I have no answer.
You're going to think about a manifold, for example.
Right, so let's say it's a manifold, some solution set to some equation. So how do you make, what is the dimension of the manifold? How do you make sense of that?
The local dimension.
Okay, there is the idea of a local dimension of somehow making out of coordinate patches. That's true. This is not the one I will be able to imitate, but other ones. So tangent space, right? So dimension of the tangent space. What is the tangent space? Well, the tangent space is a bundle, right? And the kind of the functional view of a bundle is to look at vector fields, right? Vector fields which are tangent to your thing. And then you could say the dimension, let's say the dimension is D. D will be the dimension of sorts of this space of vector fields. Only the space of vector fields, of course, is an infinite dimensional algebra. So you have to do some, or not algebra, but infinite dimensional space. So somehow you have to do a relative dimension. So it has to be dimension relative to something like, and let me just say functions on X, not to be very precise about what I mean, right? So you need to have some kind of relative dimension where the normalization is that if you look at the dimension of the function space itself, that should be 1. And then, the vector fields are something like, you have the coefficients of the vector fields and so forth. So that should be some dimension n, right? So that's one idea. Of course, these vector fields can be viewed as derivations from this space of functions of x to functions on x, right? Because given a vector field, you can always differentiate a function with respect to that vector field. And in fact, if you choose your functions correctly, all derivations will end up corresponding to vector fields. So that's nice. There's another way to think about vector fields, namely, if you take some vector field, how will it look like? Well, it will look like some a of x, right, times d over dxj, right, j from 1 to n, because, of course, we have our tangent space to the entire Rn, right, and so each time live in some kind of a subspace. And so these vector fields, they actually are a subset of just, let's say, L2 of Rn to the power n. These are all vector fields, say L2 vector fields on Rn. But of course, not every vector field on Rn is tangent to our manifold, right? And why is it not tangent? Well, because it can have a destructive effect on our relations. In fact, one of the things that a vector field should do is should preserve relations, right? So so relations restrict what vector fields are tangent. And in fact, if you want to be precise, you can actually describe some condition on these AJs for what functions do you permit, right? And the way you would do it is you would just differentiate a relation with respect to this field, vector field, and you should get 0. Otherwise, it's a problem. Okay. So the other idea is to do some kind of a covering dimension or some kind of fractal dimension. One of the formulas that is involved in this is something called Minkowski content. And the idea is that you take n minus, and then what you do is you look at the volume of an epsilon neighborhood of x. So even if x is a very bad set, its epsilon neighborhood is an open subset in Rn, so therefore you can make sense of its measure. That's fine. It has a Lebesgue volume, and then you take the log of this and you divide by log epsilon. And so if you take some limit in for something like this as epsilon goes to 0, then this will actually give you a measure of this is your d. So how does this work? Well, basically the idea is that if you have some kind of you imagine you have a 2-dimensional space inside 3 dimensions, how quickly does the volume of an epsilon neighborhood of that thing grow? Well, basically all the growth comes from the fact that of a 2-dimensional flat thing, you make a very thin 3-dimensional object, and the volume is going to vanish proportionate to that height of the object that you've added, right? So it will be so the volume will be something like proportionate to epsilon to the power 1. So if you look at log of it and divide by log epsilon, you get 1. And so when you subtract it from the ambient dimension, which is 3, you get the dimension of the space, which is 2. And you can see that for nice objects, this works very well. And so certainly for our algebraic surface, this yields the same thing. Now, this is not a very convenient thing from the point of view of free probability or probability theory, because you're referencing somehow volumes of epsilon neighborhoods of a set. What are these? So Voiculescu had this idea to replace and write a different formula. Again, let's say it's ln for something like this, epsilon goes to 0. And here, instead of this log volume of an epsilon neighborhood, you do the following thing. You look at the classical entropy, let's call it H, of mu convolved with and let me just call it mu epsilon divided by log epsilon. Well, I'll take epsilon 1/2. So what is this? Mu is some fixed measure on X. So right now, rather than talking about sets, we'll talk about sets with a measure on them. But if you have something like an algebraic variety, whatever, it's natural to have a measure around anyways. What is this new epsilon? This is the Gaussian measure on Rn of total variance epsilon times n. So it's an n-dimensional it's an n-dimensional measure, and the total variance of it is like this. And then when you convolve it, you can think of taking your coordinates x1, xn, and replacing them by x1 plus epsilon, so g1 epsilon 1/2, xn plus epsilon 1/2 gn, where g1, gn are Gaussians. And so these are somehow new random variables that you construct. And what is this entropy H? H is just the differential entropy integral of rho log rho d volume on Rn, where rho is the density of mu convolved with mu epsilon. So it turns out that for nice measures, this quantity here, this quantity here is comparable to this log volume. And so, well, apart from a change of scale, because here it's like an epsilon to the 1/2 neighborhood as opposed to the epsilon neighborhood. But anyways, this whole thing tends to behave like that whole thing. And so it's a kind of a Minkowski quantum. So there are at least two ways to define dimension. One is kind of algebraic, having to do with vector fields, derivations, and so forth. And the second one is this entropic way of doing it. All right, so let's leave the classical world. What about the non-commutative case? Well, we replace functions of x by something like an algebra and a trace, which is sitting inside some phenomenon algebra with a trace. So think of it as an algebra of some kind of functions on your space to be made precise, and this M is like the algebra of all measurable functions on your space. All right. This measure mu that's given to us, well, that's encoded by the trace. That's fine. What is a nice example? What would be the replacement of an algebraic variety, the thing that's given by generators and relations? Well, it turns out that one of the nicest things are discrete groups. So algebraic variety X with these relations R1 equals 0, Rm equals to 0. So this is replaced by a group, discrete group. G, which has generators, so G1 through Gn, and some relations, R1 of G1, Gn equals to, so identity. I mean, I could make it 0, but whatever. And Rm of G1, Gn equals to identity. Okay. So this is, I mean, many groups are finitely presented. That means they can be described as being freely generated by an n-tuple of variables subject to a finite number of relations. And so you can think of this as a kind of an analog of this sort of nice algebraic variety. And so now you can wonder what is the kind of non-commutative dimension of G. Right? So just kind of by analogy with the classical story. All right. Well, let's go with two approaches. One is the probabilistic approach. And of course, since this is a free probability school, it would be a free probabilistic approach. So Voiculescu introduced these quantities called chi and chi star. This is something called free entropy. And this is also something called free entropy. Only this is something called the microstates definition. And this is the non-microstates definition. So I assume you're not familiar with either of them, right? Is that a safe assumption? You're gonna hear absolutely nothing, so.
I believe it's the correct assumption. Yeah.
It's a correct assumption. All right. So I will tell you a little bit about both of them. But let me just say, so what these are replacements for what I called H on the previous slide, right? So I have this H, which is this integral of density rho log rho, and these are replacements for that Voiculescu invented. So I will tell you in a second what this what chi and chi star is, but basically the idea is then to define delta, which is the free entropy dimension, or maybe delta star, and this would be n minus lim sup, let's say lim infinite, depends on your conventions, as say epsilon goes to 0, and here you put chi of, and then you divide by log epsilon 1/2. And here it's exactly the same thing, only with chi star. And what do you do here? Well, remember our starting thing is that we have some algebra which is generated by some variables, let's say x1, xn, and let's say that they are self-adjoint. And we have some trace around. So it makes sense to take a free product with a semicircular family and look at this free entropy of a semicircular perturbation of your generators of your algebra. So this is very much the formula that is here, only of course here I've written a classical convolution, but as I said, I could have written it as saying that I replaced the coordinates on my variety, which is endowed with a measure mu. I replaced those coordinates with their perturbations by some Gaussian variables, right? And this is what gives me something that has as law this convolution of the measure with Gaussian measure. And same thing, same story here, right? I can take semicircular variables and use them to perturb my generators. And you could write this as, if you like, you could write this as the, you could say that the law of this is the convolution of the law of x1, xn, free convolution with some s1t, snt, where s1, sn are free semicircular of total variance Ti, epsilon. Right, so it's kind of the same object. And as I said, whatever definition of free entropy you come up with, you can substitute that there, and you get a quantity of something. All right, so what is this free entropy? Hi. So there, Voiculescu's idea was to mimic a kind of a Boltzmann definition of entropy. So say again? There's some noise or question, I don't know. I'm sorry? I hear something, I can't make out what is.
It was a sneeze.
It was a sneeze. Okay, all right. Very good. Yeah, all right. Free entropy, perfect. So suppose you're given your x, say some variables, let's say y1, yn, in some von Neumann algebra like this. So then we have their law, right? Law of y1, yn. What is this? This is just the map that takes a polynomial into the trace of that polynomial applied to y1, yn. And now we have the space of all laws. And on this space, we have the weak topology. The weak topology being the topology of pointwise convergence of a law in polynomials, right? So a bunch of sequence, if I have some laws, let's say mu, if I have some mu n's, I say they converge to mu if for any polynomial, mu n of p is mu of p, right? So in other words, when I evaluate my p in whatever variables realize the law mu n and take the trace, that those results converge to what happens if I evaluate p in whatever variables realize mu and then take the trace.
You forget a limit sign?
I'm sorry?
Did you forget a limit sign?
Yes. Yeah. All right. And now the idea is to see how many matrices there are which in this topology approximate a given law. So chi of y1, yn, actually it will be chi of the law of y1, yn. And it will be the following thing. First of all, I take the set of all matrices, little y1, little yn. These will be n by n matrices, self-adjoint, such that the law of these matrices are in some neighborhood of law of capital Y1, yn. So I fix some weak neighborhood for this topology, and I insist that my matrices are approximately in that neighborhood. Their law is in that neighborhood. So what does that mean? I fix some number of polynomials. In other words, I fix moments, let's say, to some order. And I insist that my matrices have the correct non-commutative moments to within a small error relative to the variables capital Y1, capital Yn. Okay. And I look at the set of all such matrices. Then I take the volume of this set as a volume in the set of matrices, take the log of this, take 1 over capital N squared. This is going to be the correct normalization so that one single self-adjoint matrix, you see the dimension of the space of self-adjoint matrices of size n by n is n squared, the real dimension. So this is kind of the correct normalization. And finally, I need to take some limits. I will take the lim sup as n goes to infinity, and I take the inf over this neighborhood u of this. Well, actually, I have to say it's n over 2 log n that I have to add for some technical reason. But anyways, so the brackets are wrong inside the parentheses. But anyways, it's in some sense counts the logarithmic number of matrices that approximate a given number. And so, well, maybe since we're very short on time, let me just say that in case n equals to 1, so one variable, in that case, the law is the same thing as a measure, probability measure. And then chi of a probability measure mu ends up being the logarithmic energy of that measure plus a universal constant. So this was one of the first results of Probabilistic. Okay. Now, using this, you can define delta by the formula that I already wrote, right? It will be this limit here. And again, let me not tell you much more than in the case that n equals to 1. What happens is that this delta of mu is just 1 minus the sum over t and r of the measure of t squared. So if you like, this is minus the measure of the diagonal inside R plus R. Okay. Any questions about this or anything that's then I hear nothing, so I assume everything is fine. But the problem is I can only see a very small picture of the lecture room, so I can't really see anything. All right. Great. Now, there's also the non-microstates version of chi. And here the idea is to write chi of some x1, xn as the integral from 0 to infinity of the derivative of chi of x1 plus root t s1 xn plus root t sn that derives with respect to t, right? And then integrate it with respect to dt plus, I guess what it will be, minus, plus or minus, I can't think of it. And this is very roughly the idea. So the idea is that, you see, let's actually do something a little bit more clever. Let's divide this by square root of t. And then you have to make some corrections. So there's some correction, which is something like minus n over square root of t, maybe. Because we have to adjust for the fact that we're taking a derivative not of this function itself, but of a function that's adjusted by some logarithm. But anyways, the point is that at the limit as t goes to infinity, right, this disappears and we're just left with s1 through sn. So whatever function we're putting here is going to be equal to the entropy of a semicircular system, which we just once and for all choose a value for. So there will be some error, which is some universal constant, which is more or less what happens at the semicircular limit. And then I can just, since I have a path that moves from any n tuple of variables to the semicircular variable, I can just write it, actually the way I've written is correct, right? I just write it as the integral of the derivative along this path, right? So maybe I should write in a different way. I should say that, yeah, maybe I think I'm saying it in a very confusing way. What I'm saying is that chi of what? If I evaluate this integral with the fundamental theorem of calculus, I get chi of s1 sn minus chi of x1 xn, right, is equal to this, right? You agree with this, right? Because this is just saying that if I integrate a function, then if I integrate a full derivative, I get the function back. Now, what is this dt of chi of x1 plus root t s1, xn plus root t sn? And then I have to divide, right, by square root of t. Well, first of all, it turns out that this is the same thing as chi of x1 plus root t s1, xn plus root t sn, minus n log square root of t. This is just a very simple formula that you can check about, you rescale your variables and you're computing some logarithms of volumes, and so you can easily check how this behaves. So this part is easy. This gives you n n over 2 squared of t or something like that, with a minus as the derivative. The question is, what's this? What's the derivative of this quantity? And here you have to make a kind of a leap of faith. And we know now that actually it's more than a leap of faith. Actually, the computation I will formally make is incorrect. I'll explain why in a second. But suppose it were true that we had a function f of the form identity plus, say, t little f plus O of t squared, with the property that f of x1 plus root t s s1 plus okay x n plus root t s is approximately well, is equal, let's say, f of x, sorry, 2 x1 xn. So it's a function of n variables with values in n variables. And suppose this function depends on t, and it would have this magic property that if you evaluate it on these perturbed variables, then what I would get is this in law. So same law. So I would be able to change the law of one of these things to the other. So I'm sorry, it seems that I'm running out of battery power on my PC. Sorry, we'll have to reshare my screen because of this one. I'm sorry, it's still happening. See if I can still share my screen. Different way. If not, I may ask you to admit me as a separately my iPad. So it doesn't seem to be. All right, and I'm trying to share now to my computer. Is it working? Okay, good.
Yes.
Sorry about that. You can see my screen share, right?
Yep. Yeah.
Okay, good. All right, so again, suppose we had some function ft with this property that somehow if you evaluate this f on the perturbed variables, we get new variables which in law are equivalent to the unperturbed variables. Well, from that, you can actually make a computation as to what this little f must be. So this little f is the kind of the linear term in this expansion of f. And the reason I'm saying that f should be identity plus t little f is because, well, you would imagine that since you're making a small perturbation by the semicircular thing, to undo this perturbation, you are in first approximation just keeping the variables as they are, and then you do some kind of further perturbation. So that's why it should be like identity plus something. Anyways, it must be some f, which is some n tuple, right? C1, say Cn. And what must happen is that if you take the L2 inner product between Cj and any polynomial in x1, xn, this should be equal to this expression, where these dj's are Voiculescu's non-commutative difference quotients. And this already appeared in the previous talk, right? This is the kind of stuff that appears in Ito calculus when you do multivariable Ito calculus. For that. These dj's are derivations. They're derivations from the algebra generated by x1, xn. to the algebra generated by x1, xn tensor itself. And they're determined by the following rules. The derivative of xk is 1 tensor 1 if j equals to k, otherwise it's 0. And you have the Leibniz rule. So let's say AB is equal to A dj of B plus B dj of A, right? Where this A is acting here on the left, and this, oops, where to go, right? And this B, and this B is acting here on the right. Okay. Well, so long story short, this is the derivative of this, what we've just described. After some computation, you get that if you're interested in the derivative of this chi of x1 plus root t s1, xn plus root t sn at t equals to 0, one expects to get the sum of Cj squared, 1/2 j from 1 to n and with a minus, where Cj is our unique variable, unique elements of L2 of the phenomenon algebra generated by x1, xn, such that star holds, and star is this equation. This equation. So this was this was sort of Voiculescu's idea in his non-microstates approach. So this is a kind of formal and possibly, and in fact, we now know is wrong in the sense that it is not true that the derivative of that quantity is always equal to this quantity there. I will comment on that there, but it does not prevent you from, in principle, making a definition with of free entropy using this. So you can now define a new free entropy, which is the integral from 0 to infinity. And well, what you'll end up doing is this minus this sum 1/2 Cj t, let's say, squared plus some normalization factor. Let's put a plus here, but minus it's n over 1 plus t dt, where Cjt are unique variables in L2 of x1 plus root t s1, phenomenon algebra generated by xn plus root t sn, such that this star holds. And again, I don't have time to explain, but in fact, there's a formula for this one. Namely, this is 1 over square root of t times the conditional expectation from the phenomenon algebra generated by x1, xn, and s1, sn, onto the phenomenon algebra generated by x1 plus root t s1, xn plus root t sn of sj. So in fact, there is an explicit formula, well, not explicit, but there is a formula which explains in particular why these things exist. And all of what I've said so far is in Voiculescu's paper on free entropy dimension, the non-microstates approach to that. And so, of course, as I told you, you can define delta star via chi-sec. All right. So comments, when n equals to 1, so in other words, we have one variable exactly, Voiculescu actually proved that these things are the same. And so, of course, delta is equal to delta star. So that's easy. There is actually nothing new. For n bigger than 1, there is, in fact, an inequality saying that chi is less or equal than chi star. This is a very deep result of Bian, Capitan, and Guillemet. If you like to sort of understand why this inequality holds, I can give you a 10-second explanation, which will either make sense or not. But then since it's 10 seconds, you can forget about it. Basically, this formula here, the one that I tried to, or this approach here that I did by trying to find some function that does this and that and so forth, it actually works perfectly well to connect the entropy of a random matrix model to compute it in terms of the associated derivatives like this. And the problem is that the function f that you get is a function which depends on all the entries of the matrix. However, what free probability predicts, so what its competitor Xi that you see from free probability, so the large n limit of that function, it is not a function of the entries of the matrix. It's a function that you can obtain by taking products of matrices and taking the trace of a product. And you're not allowed to do much more than that. And so because of this, when you write things in this way, the free probability computation of this Xi involves conditioning on some kind of an algebra, which gets enlarged if you do it in the finite n computation. So it gets enlarged when you go to the random matrix model and the computation of entropy for matrices. So therefore, the norm of this guy gets bigger because you're conditioning onto a bigger algebra. And since its norm, there's a minus sign, which I messed up, of course. There's a global minus, which I forgot to put. And since because there's this global minus sign, making these norms bigger makes the whole entropy smaller, and that's more or less this equality. And now it turns out that this inequality can be strict, and that's a recent result of Vidic et al. About the fact that there exist von Neumann algebras which do not have what's called a Korn approximate embedding property. And in our language, it just says that there exist non-commutative laws which are not limits of laws of matrices. So unfortunately, because of this, we know now that the two entropies must be different, because of course, if you have no laws whatsoever that you can approximate with, your entropy is minus infinity, whereas you can check that the moment you do a small semicircular perturbation, the chi star, the non-microstates entropy, would be fine. All right. So what are some facts about delta star? Delta, very well behaved. It is an algebraic invariant. So if you're given some kind of an algebra A and a trace, A is an algebra, it's a star algebra, sitting inside some von Neumann algebra, so this trace has to be positive, then you get some delta of generators of A, but actually it is the same as delta of just the algebra A. I'm lying a little bit. There's something called delta zero, which is some technical modification of delta. And this was proved by Voiculescu. In particular, now a very nice example, which we did, I told you this kind of the non-commutative algebraic variety analogy. If you look at the case of a group, you get the group algebra and the group trace. you get some invariant, delta naught of G, invariant of a group. You can easily compute the delta naught of a free group on n generators as n, delta naught of something like an abelian group, G is 1 minus 1 over the order of a group, and various other things like that. What about delta star? Well, delta star we know is bigger or equal than delta. Why? Because well, if you look at the formula, wherever that formula is, here, right? Notice that for small epsilon, this guy is negative. So if you make this entropy larger, then once you divide it by a negative number, it ends up being smaller. But then if you subtract it from n, the result ends up being larger, right? So del star is bigger. Embarrassingly not known is delta star an algebraic invariant. That is not known. But fortunately for a group, there is an equality that is known, and this is the last thing I want to prove, or at least tell you about. It has this formula, which actually is the same thing as the dimension over the group von Neumann algebra of the space of derivations from the group algebra into L2 of the group, tensor L2 of the group. So notice this is a bit like vector fields. And so this is a bit like saying that for a nice smooth case, this kind of entropic dimension is the dimension of the tangent space. So what's involved in this? Well, basically, y is delta star of Fn equals to n. Well, this group algebra of Fn is generated, I will cheat a bit, it's generated by unitaries U1, Un, which are freely independent. So you can define derivations on CFN already, such that, let's say, delta J of UK is delta I equals to K, and then it will be 1 tensor. Well, let's do something like that. You have to correct a little bit because they're unitaries. And then you can check that actually 0 satisfies the equation that 0 dot product P is equal to 1 tensor 1 delta JP for any J. So this C is just 0. And because you already have a nice C for your generators, if you now look at some kind of what would be semicircular perturbations or the appropriate perturbations in this case, these also have bounded C. And from that, you get that the entropy of this U1T, UNT is nice. So it's finite as T goes to 0. So somehow having these nice derivations gives you a fact that this entropy behaves nicely as T goes to 0. I don't really have time to explain, but in general, you write this del J, so you have some x1, xn, and then you're interested in x1 plus root t s1, xn plus root t sn. You write this del J of x1 from the algebra generated. Let's call this xt. xtn. But you write it as del j equals to del j1 plus del j2, where here you use a nice derivation from the derivations from your group into L2 of the group. And here you just take del j minus the nice derivation. And just this very silly decomposition, which is analogous to saying that an arbitrary vector field on Rn you can decompose into a tangent one and one that's normal, gives you some estimate about behavior on chi of x1t, xnt, as t goes to 0, that actually, when you combine it appropriately, gives you an upper estimate. From that, you get that del star is bounded from above by this number. And now the lower estimate, this comes from analysis of relations. So delta star bigger than comes from analysis of relations. And it's literally the following idea that we need to compute the conditional expectation on something like this of Sj, right? This was one of the formulas for this crazy C that I wrote for you. This is the formula that I'm using. And well, how do you estimate this? Well, the idea is that if you have a relation that holds for x1, xn precisely, then if you substitute x1t, xnt, you do a bit like what was done in the previous talk. You write this as a power series expansion, if you like, in T, and you get that this is the first order power of x1, xn, which is 0, and then you have T, and then you have somehow the sum of partial derivatives of your R acting in the sense like in the previous talk on Sj, and then you have high order terms. And so the point is that this is 0, and so what you get is that the sum djr hash sj is, well, it's something that is in this algebra generated by x1, xt plus a correction of order t squared. So what you really need to do is to estimate that. So instead it's t1/2 and this is t. Anyways, so it means that this is what I proved, right? Because so if now I take the conditional expectation of this, I will get that plus the conditional expectation of something that is of order t. But now if I divide by t1/2, I will still get something nice, and then here it will be already something of order t1/2, which still vanishes. So by that, I get some kind of an estimate, well, not on Sj, but at least on this complicated expression. And then if I apply some pseudo inverse and so forth, I can actually prove that some pieces of this Sj belong to the algebra, and that gives you the lower estimate. Anyways, this is all kind of technical, but my point is that it really very much resembles the way you would prove in the classical case why the tangent space decomposition into vectors which are tangent to your variety and things which are perpendicular to your variety gives you estimates on this thing. So let me just finish with some open questions. Delta star algebraic invariant. This is really an embarrassing question of sorts. And actually, the other question is, what is actually delta naught of a group? We've proved that delta naught of a group is bounded by this by this number, but when does equality hold? So for example, is this enough? Just assuming that the group has the cone-approximate embedding property, would that be enough to prove that the two numbers are the same? So that really is a question of how good are these non-commutative algebraic varieties versus what you would expect. All right, I'm sorry I went over time and I tried to compress probably too much in this talk, but what's done is done. And anyways, you have the banquet, as I said. So thank you so much.
Are there any questions for Dima? One of you two has to decide who.
I can't hear anything if there are any questions or anything like that.
Hey, Dima, can you hear me?
Hey, Dima, can you hear me? No? There's a red light.
I think I saw some microphone being passed around, but I can't hear anything. So I see what from the back looks like Brent Nelson pointing at something.
Can you hear me?
I see a question being asked. How many mathematicians does it take to unmute a microphone?
Muted? Can you not hear me?
Yeah, it's not me.
Dima, are you able to hear me?
It's not on our side.
Chat, make sure his computer audio is on. Or ask other participants, chat to us if you can hear us. Okay, great.
Okay, somebody said, I mean, anything is interesting, I think, in this setting. And I mean, especially now that we know, for instance, that the free entropy dimensions are different, right, depending on the microstates and non-microstate story. It's quite fascinating how that plays out, right? And it's entirely conceivable there are other quantities which in some cases are all the same and in some cases they aren't. In fact, you know, there are other ways to define dimension, which I'm working on, and again, I'm not completely sure that this number will always be the same as this. So yeah, I think it's very interesting.
Thank you.
Dima, can you hear me?
Yes,
Okay, great.
but not very well.
I had a question about this result of Vidic et al. That you quoted about one-moment algebras which don't have approximate embedding property.
Right.
I'm wondering if you're talking about the MIP star equals RE paper or?
Yes, exactly. That's the
Okay.
sorry.
Thank you.
Other questions? Okay, I don't see anything in the chat. All right. Seems like everybody's hungry for the banquet, so let's thank Dima one more time.
All right, thanks. And I'm sorry to be missing the banquet with you. I hope to see all of you some other time. Thanks.